Hi everyone, welcome to our webinar today. The topic of this webinar is Improving Energy Resiliency with Flow Batteries. This webinar is a presentation of Clean Energy Group's Resilient Power Project, and it is presented in collaboration with the Northeast Electrochemical Energy Storage Cluster, also known as NESC. We have an excellent guest speaker with us today. Before I pass it over to them, I'd like to go over a few quick housekeeping notes. All of our participants for this webinar are in listen-only mode. You have a couple of options to join the audio portion of this webinar. You can either call in using your telephone or you can connect using your computer mic and speakers. A very important note, we ask that all of our attendees please submit your questions as you think of them throughout the webinar by typing them into the question box on your webinar console and hitting send. We will be reading through your questions as they come in, and we will get to as many as we can during our Q&A at the end of the webinar. So please don't wait until the end to submit your questions. We'll be reading through them throughout the webinar, and we will get to as many as we can at the end. A final note, this webinar is being recorded. You'll find a recording of this webinar as well as our previous Resilient Power Project webinar on our website at resilient-power.org. And we'll also send you, as a follow-up email within about 24 hours, a copy of the recording and the slides. So with that, I would like to pass it over to our host for this webinar, Todd Olinsky-Paul. Todd is a project director here at Clean Energy Group, and he will be introducing the topic of this webinar and our guest speaker.
Thanks very much, Samantha. Welcome everybody to the webinar. This is Todd Olinsky-Paul with Clean Energy Group, and I would like to give a little background on our organization and our Resilient Power Project before we introduce our speaker and get on with the webinar for today. So in case you don't know, Clean Energy Group is a nonprofit. We're located in Vermont. We work with states, municipalities, developers, and governmental and non-governmental organizations all over the country to enhance and support clean energy solutions. And this particular webinar is done under the auspices of our Resilient Power Project, which, as you can see on the screen, is supported by a number of foundations who are kindly lending us their support. And the project is dedicated to the idea that we should have clean, resilient power, backup power behind the meter at critical facilities. And by clean, resilient power or backup power, what we generally are referring to is technologies that can be islanded from the grid in case of an outage to support critical facilities. And that would include things like first responder facilities, hospitals, communications hubs, transportation, fueling, fire, police, anything that is critical to the community in case of a natural disaster and accompanying grid outage. If you could just advance the slide, please, Samantha. So we work with a number of organizations and we produce a lot of material. You can see here on the bottom of this slide that several of our recent reports on fuel cells. We have a bunch of reports on other technologies as well. We do webinars such as this one frequently. If you're not on our list to receive announcements for future webinars and reports and other publications, you can go to resilient-power.org and sign up for our email list. And you can also search through our library there. All our materials are available free for download, and our webinars are recorded and posted in their entirety, so you can go back and review this webinar, or you could watch earlier ones that you may have missed at any time. Next slide, please. I want to thank the Northeast Electrochemical Energy Storage Cluster, NESC, for their support. We're doing this series of webinars under a contract with them, NEISC is a network of industry, academic, government, and non-governmental leaders working together to help businesses provide energy storage solutions. Next slide, please. So with that out of the way, I'd like to introduce today's guest speaker, Adam Rauerdink. And he is Director of Sales Engineering at Vionx Energy, which is a leading supplier of grid-scale, long-duration flow battery systems. So that's the topic for today. Adam directs the company's global sales strategy and project development. And prior to joining Vionx, he was the Vice President of Business Development at SustainX, which is a compressed air energy storage company. He's a graduate of the PhD Innovation Program at Dartmouth's Thayer School of Engineering. Next slide, please. So before Adam gets started, I just wanted to remind everybody of a couple of things. First of all, we will be taking your questions and comments after the presentation. We have a good number of attendees. There's 102 people attending at this moment, so I would expect a good number of questions. You can help us out by sending your questions in early. Don't wait till the end. If something you have a question about a slide or something occurs to you during the presentation, type it into the question box on your webinar panel, send it in, and as soon as the presentation is concluded, we will begin fielding those questions with our presenter. We'll get to as many of them as we can, and the earlier you send them in, the better. Also want to remind everyone, because I always get this question, yes, we are going to be posting this webinar to our website soon after it is complete, and you will be able to download slides or watch it in its entirety with the audio at that time. Okay, thanks, and I will now turn this over to Adam, and take it away, Adam.
Thank you very much, Todd and Samantha, for organizing this, and thank you all for attending. As I mentioned, I am Adam Rauerdink, Director of Sales Engineering here at Vionx. I'm at our corporate headquarters today, which is in Woburn, Mass., just about 20 minutes outside of downtown Boston in Massachusetts. I'll talk today a little bit about the technology behind our company, the corporate history of the company, as well as the projects and products that I'm responsible for bringing to market. Starting that, a little bit of just laying a picture of where does Vionx sit within the storage world, and how are we differentiated within our particular sector of the storage market. Really, where we are focused on is bringing to market a 20-year life product, a product that could be paired alongside traditional grid assets, or could be paired alongside wind or solar, but has a lifetime that is comparable to those assets. So where you're measuring the lifetime in decades, rather than years or tens or hundreds or thousands of cycles. In that space, focused on long duration, that's really where flow batteries play best. Here it says 6 to 10, really focused on 6 to 10, some projects at the 4-hour duration. But an important thing to note about flow batteries is that you do have, it is an electrochemical solution, it's inverter-based, and so while many of the applications are energy-focused or have an energy use at their core, the ramp rates of this technology are still sub-seconds. So all of the power applications are very much within its capabilities, and as you start to piece together projects and compile revenue streams, you can really take advantage of both high energy use cases and high power capabilities. But at its core, you're always having really a need for an energy battery, and that's where we play. And an important differentiator between when you look at some of the lithium-ion, for instance, or lead acid, is that our battery, you have lasting capacity. So if you buy a 10 megawatt-hour system, you have 10 megawatt-hours for the life of the project. There's no degradation, there's no replacement needed of cells or augmentation over time. And if you look on the screen here, I know the topic of the webinar is resiliency. Here is one of our systems that's sponsored by the U.S. Army. It's sitting at Fort Devens in Massachusetts, 160 kilowatts, 640 kilowatt hours, so a 4-hour battery, and that is operating in a behind-the-meter facility alongside a solar installation that's not on this picture. but behind-the-meter use as well as resiliency use. So very relevant to the topic of the webinar. And I'll show you some of our other projects as we move further in the presentation. Something that's quite unique to Vionx is really the background or the history of the technology, as well as our reliance on really a world-class team of strategic partners. And I'll mention a few of those here. On the equity side, a number of very relevant partners, United Technologies Corporation, which is really the source of the technology. This comes directly out of the fuel cell work that is quite well known historically from UTC, decades of work in that field. We work with a key number of project engineers at the United Technologies Research Center. Those that were many of them have fuel cell backgrounds, about 30 years of fuel cell work that happened at UTC. They then took that learning and applied it to flow batteries, and then that learning was in turn exclusively licensed to Vionx. So UTC is really the source of some of the core technology behind the company, but they also remain an equity owner in Vionx, and we have them on contract in a ongoing basis as our R&D arm. So Vionx, where I sit here, is really focused on system engineering, but all of the advanced research and development on new materials and new chemistries, and as well as supporting our engineering team, that is all taking place at their facility in East Hartford. So a very, very strong relationship with United Technologies Company, and it applies in many different fashions. Some other core partners that come to bear in the product, the membrane, which is one of the core critical elements of the system, is from 3M, and we have a very close relationship with 3M in both developing or bringing to market the current membranes, as well as working with UTRC on the next generations of membranes. The systems are manufactured by Jabil, one of the largest contract manufacturers. We currently come out of a facility in St. Petersburg, Florida, but Jabil is the one constructing the projects and then shipping them ultimately to the customers. At our facility here, we have a small manufacturing space, but that is something that's quite unique to flow batteries, certainly when you compare with lithium-ion. It's just the infrastructure, the very limited infrastructure needed to manufacture the batteries, and the light capital needs to produce batteries at very large scale. Siemens we've worked with to date on the 3 projects that you'll see later in this presentation, providing the EPC on really the AC components of the system. Also of note on the equity owners are Starwood Energy Group, who we work with very closely on the project development front. Next slide here really gets into the heart of the technology, what differentiates Vionx, and how do those partnerships with major customers or major partners come into the product. So here you'll see what we call the stack, which is really the power portion of the product, where the electrolyte is reacting where power is being generated. So when you scale a flow battery in terms of power and duration, the stack is what's determining the power of the system, and you'll see that in the product later. And the volume of the electrolyte is what's determining the energy of the system. So if you're going from a 4-hour system to an 8-hour system, you're doubling the quantity of electrolyte. If you're going from a 1 megawatt system to a 2 megawatt system, you are doubling the number of stacks. But within the stacks, that's where the technology from United Technologies and the membranes and materials from 3M are found. So one of the key innovations that the UTC developed over its years, and this comes directly from the fuel cell work, is what we call the interdigitated flow field. So if you go back historically, flow batteries have had troubles in the past with leaking. If you ask people what has been their experience of flow batteries or what has held flow batteries back, leakage is one of the key elements, and that typically had to do with operating at high pressure, and operating at high pressure in order to get high power density out of the system. What UTC developed was, again, what we call the interdigitated flow field, which allows the electrolyte to have very close contact with the membrane so that you get high power density out of the system, and to achieve that at low pressures. And so that really comes down to fluid engineering and fluid flow and how those parts are created. If you were sitting in our conference room here, you would see it on the table. It's a very simple part in principle, but it has a critical importance in terms of how the system operates, in terms of its ability to have the stack, as I mentioned, at low pressure, at high power density, and a stack that can deliver reliable power for 20 years without wear on the seals, without wear on the membrane. So that is something that is somewhat differentiating for Vionx, in that the stacks are designed for a 20-year life. They are not a replacement item. You're not tearing down the stacks to replace membranes at multi-year intervals. It is a system designed really around 20 years. That's the components, that's the membranes and the stacks, and that's the electrolyte. All are there for 20-year life. 3M provides the membrane, and this is something that they commercially manufacture today. So very, very large manufacturing capability, as well as proven performance from the membrane. And if you're interested in learning more about some of these components, we have had the system independently validated by DNVGL, and under NDA, that's a report I'm happy to share with potential customers. This chart here shows some of the performance validation behind those 20-year claims. So the Vanadium Redox flow battery has been around for decades. If you go to Japan, for instance, the Sumitomo Electric has had systems in the field for nearly 20 years. And one of the core performance validations that we're looking for, or that a customer is looking for, is how does the system's capacity and performance behave over cycling. So here's a plot from our lab of 10 of the commercial scale stack cells, which have been cycling. This chart's at 10,000 hours. They're now closer to 12,000 hours. But you can see over 10,000 hours, over 3,000 cycles, and less than 1% of performance degradation. And with the chart and the data here is electrical performance, and so you can see the steady performance there. We've also done validation on the materials, so taking the stack apart and looking at electron microscope views of the membrane to see that there's no wear. Also looking chemically and validating that when you look at the electrolytes, that the quantity of vanadium is there, that you're not seeing contaminants showing up in the electrolyte. So really validation on three fronts, and from the customer's perspective, seeing it in terms of the electrical performance that's going to be directly impacting the value and the financial performance behind a product. Brief note here on really where Vionx sits and where we are compared to the whole spectrum of storage solutions, and then in particular in those that play really in the long duration case. So if you look historically at what's dominated energy storage on the grid, and in particular what's dominated the long duration space, that's certainly the majority of that is pumped hydro. Also a few examples of compressed air energy storage, both of which are very commercial, have decades of performance in the field, can be quite cost effective, and can last for decades. The big issues there, why you haven't seen compressed air take off and why you see pumped hydro being very limited in where it's being built, is the geographic constraints. Where do you have salt? Where do you have proper elevations and environmental conditions to allow pumped hydro? So very, very limited in where it can be applied, but it is being built, and it can be built cost effectively. What Vionx delivers is really that ability to deliver long duration, but to do it in a distributed fashion, where you can provide megawatts or tens of megawatts of power and 6 to 10 hours of duration, but being able to do it at that sort of scale and being deliver it close to where the value is needed, not being tied to geology. Lithium ion is certainly outside of pumped hydro. It certainly dominates the market today. But really, when you look at where the application's focused, it's sub-hour applications, similar to what we just saw in National Grid's tender in the UK, or applications really up to about the 4-hour duration length, as you might see in California. But once you move beyond that, that's really where the flow batteries really start to take the economic lead. There are a number of other technologies in the long duration space being developed, different chemistries, different materials, and a lot of those do hold promise in the future. But what really, I think, differentiates Vionx from those advanced or those alternative flow battery chemistries is the ability to deliver a product today that has proven performance, that has proven materials, and that can be delivered at scale. And that really comes down to our reliance on a world-class consortium of partners, and that's central to that advantage. As I mentioned on the first slide when we introduced kind of the 3 bullet points behind kind of where does Vionx fit, 20-year life, long duration, lasting capacity. When you start to look at that, here's a comparison over a 20-year project life versus lithium-ion. There are a lot of, some of the finer points of this we can certainly debate around in terms of degradation rates and cost declines, but just laying out here on this slide is the general principle of how does if you look at a flow battery and a lithium-ion battery that have comparable upfront capital cost, which you see on the left, what does it look like over a 20-year project life in terms of overall lifetime cost? So the first column you'll come to next is the column where the lasting capacity and the 20-year life really shows up in terms of an advantage. If you look at lithium-ion, you are either faced with overbuilding it initially, limiting depth of discharge, augmenting cells over time, or wholesale replacements of cells at certain year intervals. And that can be quite a sizable cost. We see one example of it here with overbuilding, augmentation, and replacement built on, the numbers here are based on some public RFP documents that we have seen. Maintenance, there are more moving parts in a flow battery compared to a lithium-ion battery, so you do see a slight advantage for lithium-ion there. And again, in operating expenses, really where the round-trip efficiency of a system comes to bear, you'll see an advantage to lithium-ion. When you compile all of that together, though, into a full project pro forma over a 20-year life, you can see that lost energy recovery, the cell replacement, that's really where flow batteries will pull ahead. And that's especially true when you really get into high-energy applications and in the 6 to 10 hour space. And that is really where we're focusing, and those are the core reasons behind that corporate focus. At the end of the webinar, we'll have questions, so I'm certainly happy to dig deeper into the technology and some of the particulars around our relationships with those different partners. But on this slide here, I'll move into a bit on our projects, the projects we've done to date, and a few of them that are under construction right now. I mentioned on the first slide our first project that was commissioned late last year with the U.S. military in Fort Devens, Massachusetts. That's a 160 kilowatt, 640 kilowatt hour system, 4-hour duration. And that system is online today. We give tours very regularly over at the military base there. Our second project, which will be coming online in the next several months, is under construction right now in Worcester, Massachusetts. If you're familiar at all with the town, you may have seen the wind turbine at Holy Name High School. You can just sort of see that in the picture here. It's directly adjacent to that on the Holy Name High School property. That's a 500 kilowatt, 3,000 kilowatt hour system that will be operated by National Grid once it's been commissioned. As I mentioned, that's operating alongside wind on a local feeder. A second project with National Grid is coming online later this year. That project will be more closely linked with solar, but the size is comparable, 500 kilowatts, 3,000 kilowatt hours. Moving forward, the next projects in the project or in the product that I am most closely focused on selling is the system you see here, the 1,000 kilowatt building block. It's important to note that the stacks and the electrolyte that we've used in the projects I showed on the previous slide, it's identical, comparable, the major system components. What's really being changed is how the system components are arranged. So in these pictures you see on the slide here, again, this is a 1 megawatt building block. The two central containers are the power components, stacks only. So all of the stacks, all of the pumps, all of the moving components are located in those central containers. All of the containers around the periphery are liquid tanks only. So that is the energy component, the electrolyte. So if you want to move from a 4-hour to a 6-hour to an 8-hour to a 10-hour system, you're adding in additional electrolyte tanks. And that's also something that can be added in over time. You can install a 4-hour system and add additional electrolyte volume in future years to enhance the duration of the system. But really what our engineering team has been focused around is putting all of those components in as tight a possible space ensuring reliability in terms of how the components are laid out, and redundancy, and where the wear items are, and ensuring that when maintenance events do pop up, that the system can be brought back online very quickly, so that the time of recovery is very short. And throughout all of this, ensuring that one of the key regulatory questions people ask typically is how is the electrolyte handled? And so in the system you see here, there's no additional exterior berms or anything of that sort needed. The electrolyte within those containers is double-walled, and that's really the big requirement, that there be double-wall containment around the electrolyte, and that's integral to those containers. Anywhere where the electrolyte is traveling to the stack container, there's double-walled piping, but the arrangement that you see here keeps the footprint tight and also keeps all of that piping to a minimum, which helps with cost and helps with efficiency and performance of the system. Here's a few more. Here's a few specifics exactly on how the systems can scale for different durations and what that looks like from a building block. Those renderings on the top, as I mentioned, two major components: the power portion of the system, those central containers, and then the containers around the perimeter, which are the energy duration. So you'll see a 6-hour, an 8-hour, and a 10-hour system on the top. All of these are 1 megawatt. So the difference is only that you're adding additional electrolyte volume around the perimeter. AC efficiency of 68%. That includes all the way out to AC on all the auxiliary and heating and cooling loads. And as I mentioned, a 20-year life at unlimited cycling, and the rest of the performance criteria can be seen there. Just for scale, I forgot to mention on the previous slide, you're looking at about 40 feet by 50 feet for that 1 megawatt DC block. Moving from the projects we've done to date and the product that we have to looking ahead at where are we focused on the marketing front in terms of the applications we're going after and the customers and channel partnerships that we're developing. At the beginning of the webinar, we talked a lot about, or Todd mentioned, focus on resiliency, and that certainly comes to play in all of these applications. It's certainly relevant in the commercial and industrial space. We have the project with Fort Devens. We are also working with a number of large industrial customers for behind-the-meter applications, again, really because of the scale of our systems, really a megawatt focus and up. But most of our focus, I would say, is really in the utility scale applications. So whether it be with utilities for T&D applications, whether that be investor-owned utilities or public utilities, where they're a bit more vertically integrated and you can combine T&D value and generation value as well as end-user value. And the third bin would really be the whole focus around renewables, whether that be wind or solar, and that can be both on the mainland grid or in a microgrid environment. But I'll talk in particular about focus on solar plus storage and what sort of product we can deliver and what the opportunity is. If you're familiar at all or been following at all what solar has been doing in price over the last couple of years, you've seen that it's repeatedly beating the forecast for where the price is going to be. What that allows is very, very low cost and distributable charging power for storage. And so we see a very strong opportunity in working very closely with a number of channel partners in being able to deliver a combined solar plus storage product to really deliver to the customer a dispatchable 24/7 solar product. It's a market that really to date had been a few applications of concentrated or CSP, but again, that's a solution where it's typically hundreds of megawatts in scale. By solar and storage with a distributable kind of megawatt block, you can bring that sort of a product type, again, a dispatchable solar product, really a dispatchable peaking plant to the grid in the megawatt scale or tens of megawatt scale, and do that quite cost effectively. So if you look at what we can deliver today, a dispatchable product around 15 cents per kilowatt hour in terms of the output energy, and by 2020, based on both continued cost reductions in solar and continued cost reductions in the Vionx product, delivering a combined energy product at about 10 cents per kilowatt hour. And the basics of what that product looks like is shown in the central plot here. So looking at the typical solar day, where this is focused on an island application where you have limited load, you can continue to build the solar, but eventually you will realize curtailment, or you'll realize limits on minimum generation from diesel. What the solar plus storage product allows you to do is, most are familiar with this, but store that excess solar energy and then distribute it throughout the day. The important part here is that the high energy applications, so we're moving beyond just simply smoothing to help make the diesels more efficient or reduce cycling. We're really allowing diesel to be turned off, and we're really allowing tens of percentage reduction in when diesel is utilized. So the basics of the application are that solar directly to grid is used whenever it can. All of the rest of the excess solar is stored, shifted either to the nighttime peaks or into the morning hours. And what you have is really flexibility there in how you dispatch that power. And that's something when you look at regions of the grid where they are burning diesel at 25 cents or 30 cents or more, much more in some locations, it's very cost competitive today. And when you look at regions of the mainland grids where you don't have easy access to building out new transmission or distribution or building out gas pipelines, it again can be a very, very cost-effective solution, and something that we are working on projects at tens of megawatts scale for next year. Walk through my slides fairly quick there, but I wanted to leave some time for questions, so I'd be happy to do so.
Okay, thanks very much. That was it's quite informative, and we do have a lot of very good questions. So I think we'll start with somebody, well, there's two related questions. One is if you could just please give a simple explanation of how the battery actually works. I know we've done that in previous webinars, but obviously, not everybody attended those. And then a related question is, do you have a good technical report or paper you can provide on the technology to help people understand better the advantages and disadvantages?
Sure, happy to address that. Yeah, I didn't have any basic intro slides in here. So the basic, as I mentioned a bit at the beginning, there's kind of two or three major components to a flow battery. So you have the liquid electrolyte, that's the energy portion of the system. You have the stack, which is really the engine of the system. That's where the electrolyte is meeting, where the electrons are being generated. And then you have a series of auxiliary systems, pumps and plumbing and valves that really control how that electrolyte is flowing. So one of the examples we typically use with people is you can think of it kind of like an engine, where the stack is the engine, the electrolyte is the fuel tank. And so if you need more power, you increase the size of your engine, size of the stacks. If you need more energy, you increase the size of your fuel tank, the volume of electrolytes you have. But what's within the stack, that's where the reaction's occurring. That's the only place where the electrolyte is actually meeting. So when the system is turned off, which this is something quite different than lithium ion or some others, the reactants are physically isolated in that commercial scale system. You saw the electrolyte was in tanks around the periphery. So when the system is turned off, valves are closed, the electrolyte is isolated, which is an important characteristic from a safety perspective, but it also ensures that you can maintain capacity, that you're not losing energy during idle times because, like I just mentioned, the electrolytes are separated. Another thing that's unique about a vanadium chemistry is that the electrolytes, both the positive and the negative, the cathode and the anolyte, are identical chemically. They're put in different charge states when you charge the system. But if there is at any point any small leakage across the membrane, you're not permanently losing any capacity from the system. You can physically shift electrolyte back to the other tanks and recover all of your volume. And then I don't have one of the pretty pictures in here, but if you look at the vanadium electrolytes, what's happening is it's moving between 4 different valence states, V2, 3, 4, and 5. There happens to be different colors for each of those, and we have some vials of that on the table here, and there's a yellow and a green and a blue, and those are very truly in those colors when you put them in those different states. But when they meet at that membrane, that's where the ion exchange is happening, and you're going from V2 and V5 to V3 and V4 and back and forth. And if you go on our website, we have a technology video there, which does a very good job of really walking through the technical advantages in terms of how the interdigitated flow field allows you to get the advantages of the low pressure and high power density. Historically, there had been different flow-through and flow-by technologies for flow batteries, each of which had their various pros and cons. And we think this is really a very strong combination of those 2 different approaches. And again, that was something that UTC developed over several decades of work on their side.
Okay, great. Somebody wants to know, well, this is quite a long question, but they point out that resiliency in many circumstances applies in small and highly distributed settings. So transmission lines have been disrupted. You have, you know, a critical facility or a particular feeder is down, and they want to know how the 1 megawatt capacity and grid placement of the solution address that issue in the real world. And then the follow-up is Vionx assessing the prospect of downscaling the solution to match smaller energy or load increments that are likely to exist?
Yes, I'll answer the second one first, which is just that today the majority product to the market is a megawatt scale building block. That is what we have available right now. We have done some smaller systems. You've seen those on the slides in the 160 kilowatt level. So that is a product that is being manufactured currently. But our shift and our focus is around the megawatt scale building block. It is possible to use, as you see, there's 2 different layers to the system. Those can be operated independently, so we can deliver a 500 kilowatt system. But that really is the lowest, the smallest building block that we can offer. In terms of market focus and locations, the attendee was very correct in their question. For the T&D, it is really a critical, very site-specific need for when you start to look at overload or contingency issues on the utility grid. It can be very, very site-specific in terms of where those applications are needed, or in terms of how the individual circuits are laid out within a town or region, in terms of where do you place the storage system to help relieve peak load, help provide power or resiliency during a contingency event, or in terms of an outage, what circuits or portions of the circuit can you keep online. So that becomes very, very site-specific, and there's a lot of factors that come into play, including what's the, based on that location, what's the cost of the traditional grid upgrade that would be your competition. That's in part where we spend a lot of time as well on applications like solar plus storage, where it can be much more broadly developed without really having to get down to those very, very site-specific criteria, as you may see on T&D.
Great, thanks. There are several questions regarding how long a duration you can store charge for using the flow battery. And one of the questions is even whether you could hold the charge for seasonal weather cycles. I'm going to guess that would not be economic to do. If you even, I don't know whether the answer is yes or no, but if you could do it, it would mean that the battery is just sitting there for months doing nothing, which is probably not an economic way to use the battery. But I'm going to, as far as what the technical ability of it is, how long can you hold the charge? And what is the, you talk about a 6 to 10 hour time. I guess that's one time, but if you could just define that a little bit better.
Sure, yeah. So in terms of what durations or what sizes of systems can be delivered. There is no hard limit there. We could deliver a 1-minute battery. We could deliver a 100-hour battery. In terms of where our market analysis has allowed us to focus is really in that 6 to 10-hour space where, you know, the functionality of the system, the use cases and economics all seem to balance. But there's no physical limitation from going, you know, much shorter or much longer. It really just comes down to how large are the tanks. And you can build much larger tanks and go much longer duration. But as you mentioned, Todd, it really becomes a question of economics. Is it really valuable as a seasonal storage application? We haven't seen much to lead it. So we focus more on heavily cycling the system. When I talk about a 6-hour battery, what I mean is that if we were to fully charge the battery, have it at 100% state of charge, a 6-hour system could run at that rated power for 6 hours. So a 1 megawatt, 6 megawatt hour battery could just charge at if you were just charging constantly at the rated power of 1 megawatt, which it can, for the full state of charge, you would be running it for 6 hours. You could certainly run it for longer at very lower reduced power levels, but at its rated power of 1 megawatt, you could run it for 6 hours for a 6 megawatt hour system, 10 hours for a 10 megawatt hour system.
Okay. So it sounds as though the advantage of this kind of thing is that you could, for example, use it to shift wind production from night to day, from off-peak to peak on a daily basis. You probably don't want to do any kind of seasonal shifting, but you could do that. You could hit say a 6-hour, maybe more realistically, a 4-hour shift.
Exactly, and that's similarly in the solar realm. That's what you see in the application we talked about for dispatchable solar. It's daily shifting of large quantities, large energy, solar energy, so high energy cycling.
Okay. So related question, somebody wants to know whether the batteries are able to handle large inductive loads in commercial buildings, and this would be things like elevators, pumps, etc.
Yeah, so that really comes back to the inverters that are chosen for the Fort Devon system. It is doing power factor correction, and it can be doing that almost constantly. So that is certainly a function of the system, and that's in part a function of the inverters. But yes, we're capable of that.
Great. A couple people have asked, what is the round trip efficiency?
Yep, so that was shown on the slide here as both a DC level efficiency and an AC efficiency. But the AC efficiency outside of the inverter, including the auxiliary loads and heating and cooling in an average environment like Massachusetts, is 68%.
Okay, so 68% is the round trip efficiency?
Round trip AC efficiency, yes. Yes.
Okay, great. Regarding costs, are the costs shown in net present value terms? Somebody is asking. I'm not sure how you'd answer that unless you had a...
In that particular chart, no, they're not. We have a bunch of other levelized cost of energy or project pro formas where everything is put into net present values. But on this chart here, they're just shown as, you know, a lifetime cost. There's no weighting in here just for ease of demonstration. But I will tell you that the advantages you see there do hold when you put it into a full financial model at 20 years and factor in all the various elements and weighting and cost of capital and the rest. But that's not what's shown on this slide now.
Okay, another related question. Somebody wants to know, are the costs for the battery based on a 20-year life and fully wrapped with AC output?
Sure. So I'll give you one number for next year and then give you some general references around trends. So for next year, an 8-hour battery system fully wrapped can be delivered for $500 a kilowatt hour. That's a full turnkey AC system, everything but land. And there is a very exhaustive cost reduction roadmap that sits within our engineering group, and that I'd be happy to share with people if they're interested, but I'm not going to talk about that too publicly. But I'll say that there's a number of different elements behind that, and volume is not a substantial element. So we can achieve very aggressive cost reductions at quite low volume, and that really comes down to the business model and the makeup of the technology.
Okay. Regarding the warranty, somebody has a couple of questions about that. Assuming that it's a 20-year warranty, does it guarantee performance? Are there any stack replacement costs included? Is the warranty built into the quoted cost, or is that a separate cost? How does that work?
So the warranty is built alongside a user having a long-term service agreement. And so the service agreement it's really a catalog plan covering any replacements in pumps, point failures in membranes, any other damages that would bring the system below its rated performance. And then it is built around a 20-year guarantee. I can give you substantial detail behind that offline. I would be happy to do so. But that is certainly a focus of the technology and something, again, where it's quite differentiating from many others in terms of being able to combine proven components to put together a 20-year guarantee around a system.
Okay, well, just so we're clear, so the warranty is not included in the battery cost that you quoted?
The warranty, if a customer purchases a battery and signs up for a long-term service agreement, which there is a cost to the service agreement, that comes with the guarantee. The guarantee is wrapped in with that. And
do we get the cost of the service agreement?
I didn't share that here, but that certainly varies with the size of the system, and it's again something I can share offline.
Okay. Also, somebody was asking about the end-of-life cost, and I think this relates to one of your bar charts. The question is, how is it possible for there to be a $0 per kilowatt hour end-of-life cost?
Yes, that's really factored in there from the recoverable value of the vanadium. So the vanadium commodity can be physically recovered. What's the price of that commodity in year 20? That's not known, but based on our current numbers and estimates, that essentially offsets the cost of scrapping and dismantling the system. That said, we talk about a 20-year life. The majority of the components, over 50% of the components, are still are still at rated power or performance after 20 years, and so with slight modifications on refurbishments, you can keep the system going well beyond 20 years.
Okay, great. So you're talking about the value of recovered materials offsetting the cost of decommissioning, essentially.
In the case where somebody was bringing it entirely offline, yes, but more likely we would see applications where you refurbish it and continue operation.
Okay. There's a question here specific to Massachusetts. What, if any, challenges are you facing on interconnection of the projects in Massachusetts?
I would say that we've had very good support from our partners to date. So worked with the Army and the local utility there, working right now with National Grid on the projects in Worcester and in Everett. So I'd say they've been quite supportive to date. So we've been fortunate, I would say.
Okay. And somebody wants to know whether the enclosure requires any climate control.
So the enclosures themselves do not, but what we do climate control is the electrolyte, the temperature of the electrolyte. So there's a liquid-liquid heat exchange with the electrolyte, and that's something that is included in that 68% round-trip efficiency number.
Okay, great. This is just my question, actually. Are there, I know you talk about cooling, but are there environments in which it may be too cold and you would need to control the temperature in the other direction?
Yeah, so the rated ambient temperature range for the standard system is on the slide here, -40 to +45 C. There's no hard stop at those levels, but you would have to custom engineer things in environments outside of those ranges.
Okay, so outside of those ranges it affects efficiency, or do you just not operate outside of those ranges?
It would certainly impact system design in terms of how you lay it out for the particular location, which certainly could have impacts on performance.
Okay. Now we've covered this, but somebody's asking what's the cost for a 1 megawatt unit. Maybe you could just run over that again, since it seems to be something people are asking about.
Yeah, so I'll give you the, repeat the same number for 2017. So an 8-hour system, 1 megawatt, 8 megawatt hour system on 2017 turnkey is around $500 per kilowatt hour. But I'd be happy to give, customized pricing for different scales and different durations and different years of delivery. I'd be happy to do so, and I've done that with numerous customers.
Great. Okay, somebody is asking how much runtime Vionx has in commercial applications, and if you could please identify any referenced installations.
So the one that is online today is that system at Fort Devens. That one's been online for almost a year now. The next system online will be the one at Worcester, Mass., which is under the final stages of construction right now. You can see a picture of it on that screen, but that will be our second system online. There's been a number of smaller test systems that have been operating either at United Technologies Corporation or here at our facility, but these on this screen are the ones that are under commercial operation today or soon to be.
Okay. And we also have somebody who is asking how is the field of flow batteries and fuel cells in terms of graduate mechanical engineers. I guess this person is looking at getting into the industry. It'd be kind of interesting to know how is that industry looking for mechanical engineers?
Well, I would say that in terms of the market prospects for the product, we see a very, very strong need. We've seen, if you look at how the energy storage market has matured over the last couple of years from applications really focused around the sub-hour and 30-minute range, now really the majority of the market being at the 4-hour range. We see that trend continuing, and once you get into that range, the beyond 4 hours, flow batteries, especially when you talk about scale, are really the solution that can fill that niche. So we see, in terms of somebody entering careers, I see a very strong opportunity for flow batteries, and that's, I think the market is certainly trending, and all of the analysts' reports would support that.
Okay. There's another question about Massachusetts in particular. So, in your wind and solar applications in Massachusetts, are you charging using DC from generation, or are you inverting to AC, capturing RECs, and converting back to DC to charge, or something else?
So in the projects you see here, both of these are existing renewables facilities, so we are charging at AC. There are a number of projects that we are looking into where we would be charging on the DC side or operating DC, so that is something in our pipeline, yes, but not for these two projects.
Okay. Does it impact the efficiency doing one way or the other?
There can be improvements in efficiency. There's improvements in overall reductions in cost, improvements in simplicity. So there's a number of potential advantages there. And that's, I mean, many of the major players, even on the solar side, in their development paths are pushing towards that, towards integration on the DC side with storage, just because of the simplicity, the cost reduction, and the potential efficiency improvements.
Okay. We also have some questions about your controls applications, your software. One is about its availability. Another is about who your key partners are for developing and delivering the controls software for the combined solar storage solution.
Yeah, so the DC battery management control software, that we've developed in-house over a number of years. We work with partners in terms of the grid-facing, the energy management system, that AC-facing controls, and that logic that we work through with partners. To date, we've worked with Siemens on these 3 projects.
Okay. I think that at this point, maybe we have time for maybe one more question. We'll close it out. I want to give Samantha a chance to announce any upcoming webinars. So I apologize to those of you who have sent in questions that we haven't gotten to. And as always, we do our best and we'll make the webinar available for review online. Just a final question. How do you see the flow battery market progress compared to other battery technologies such as lithium-ion?
Yes, I think long-term prospects are very strong, and I see significant growth starting in 2017 and growing beyond there. We expect some very exciting press releases in the next couple weeks and months ahead, and certainly very strong growth starting in 2017. So, quite favorable. That's why I'm here.
Is there something about 2017 in particular, or is that just happens to be?
Well, it's just the timing of our technology and the validation of the system and performance and really ramping up the production. So.
Okay, very good. Well, thank you very much for your presentation. I think it was quite informative. Again, I'm sorry we didn't get to all the questions, but we got to quite a few. And Samantha, do you have any upcoming webinars that you would like, or other events or publications you'd like to announce?
Sure. If people are interested in the topic of resilient power, we have a really interesting webinar series coming up on bringing the benefits of solar to affordable housing in California. Part 1 of that webinar is next Thursday, and Part 2 is the following Thursday. And you can find information about that on our website at resilient-power.org.
Okay, sounds good. I want to thank our speaker again and everybody who attended, and we'll see you next time.